My name is Dr. G.V. Rao, Professor in the Department of Civil Engineering, Vijnan Institute of Information Technology, Duvada, Visakhapatnam. Today we are going to discuss about boundary layer separation. Before going to discuss about boundary layer separation, first we should know what is boundary layer, how the boundary layer varies from boundary perpendicular to the boundary, along the boundary. Now, boundary layer, what is boundary layer first? Suppose a free stream velocity u, capital U, passes over a solid body. This is the solid body. The flow over the solid body is like this. What is happening over the solid body? This is the solid body. The water flowing over the solid body, the water is real fluid. Real fluid. Real fluid having viscosity. Once the fluid having viscosity, there is a bond between the boundary and the fluid. Because of that viscosity, the flow over the solid body is zero. Over the solid body is zero. Away from the solid body, the velocity gradually increases. Over the solid body, the velocity is equal to zero. In the vertical direction or perpendicular to the body, the velocity gradually increases. At one point, that velocity reaches to free stream velocity. Over the body, the velocity of the liquid zero, perpendicular to the body or normal to the body, the velocity gradually increases. At one point, the velocity reaches to free stream velocity. The variation of velocity from 0 to free stream velocity, that is very nearer to the solid boundary, takes place in a narrow region. This narrow region is known as boundary layer. Okay. The velocity varies from 0 to free stream velocity, and that variation of velocity takes place within the very small narrow region, that is very vicinity of the solid body. This narrow region is known as boundary layer. Now, and boundary layer thickness. And boundary layer thickness means same, the velocity of fluid 0 over the solid body, and perpendicular to the solid body the velocity increases up to certain point, where the velocity of the fluid reaches to 0.99 times the free stream velocity. That point and the boundary, the distance between that point and the boundary is known as boundary layer thickness. Right? Boundary layer thickness means is the distance between the boundary where the velocity of the flow reaches to the free stream velocity, 0.99 times the free stream velocity, the distance is nothing but boundary layer. First case, boundary layer thickness perpendicular to the solid body. Right, perpendicular to the solid body, the boundary layer thickness, this is the form of the boundary layer thickness. Boundary layer thickness along the length of the plate. Now, this is one solid plate. Smooth and thin plate provided in front of the free stream velocity. So, once the water flowing over the body, because of the viscosity, there is no velocity of the fluid over the body, right? So, this is the leading edge. So, once the water striking this edge over the body, there is no velocity. Along the length of the plate, the velocity gradually, the boundary layer gradually increases, and one point that is disturbed like this, and again the boundary layer increases. The boundary layer movement or thickness along the length of the plate, three components. One is this is the boundary layer, the velocity at the leading edge is 0 and gradually the velocity increases here. In this zone, this is a very thin zone, and the velocity in this zone is laminar, right? Therefore, this zone is known as a laminar boundary layer. Laminar boundary layer means the boundary layer very thin thickness and also flow in this zone is laminar. Therefore, this zone is known as a laminar boundary layer. Even though the main stream flow is capital U, but here the flow is laminar. The length of the laminar boundary layer zone is estimated by using the Reynolds number. Reynolds number equation, Reynolds number Re equal to rho V d by mu. Here rho is the density of the fluid, V is the velocity of the flow, d, whereas in case of pipe flow, d is nothing but diameter of the pipe, whereas in case of open channel flow, d is nothing but hydraulic mean depth. In this case, d is nothing but x, that is the distance between the point B and point A, or the distance from the leading edge to the point B. Now, the laminar zone is estimated like Reynolds number equal to 5 into 10 power 5 is known as corresponding zone is nothing but laminar zone. Now, Re is equal to Reynolds number is given 5 into 10 power 5, mass density or density of the liquid known to us, velocity of the fluid also known to us. Here the viscosity of the fluid also given, only unknown is x. The x is determined by using the Reynolds number is equal to 5 into 10 power 5, then corresponding x is nothing but boundary, that is laminar boundary layer zone. Right. This is the laminar boundary layer zone. After the laminar boundary layer, the flow is disturbed and irregular. And also in this zone, the flow is changes from laminar to turbulent. This zone is known as transition zone. Transition zone means the flow changes from laminar to turbulent. That zone is nothing but transition zone. In this case, in the transition zone, the laminar boundary layer thickness gradually increases. Yes, and another point, beyond the transition zone, the boundary layer thickness continuously increases. The flow in this zone is turbulent, irregular. Therefore, beyond the laminar zone, the boundary layer thickness gradually increases, the flow is turbulent. Therefore, this zone is known as a turbulent zone. Now, along the length of the plate, the boundary layer having three components. One is laminar boundary zone, transition zone, and another one is the turbulent zone. Right. The velocity of flow along the length of the plate goes on decreases because the cross sectional area increases. Automatically the velocity of flow decreases along the length of the plate. At a certain point, the stage may occur that the boundary layer, this is the boundary layer, this boundary layer may not be able to keep sticking with the surface, or the boundary layer will be separated from the surface. This phenomena is known as boundary layer separation. At a point over the boundary layer, at this point the boundary layer is on a verge of separation. That point is known as point of separation. That point is known as point of separation. This is about boundary layer separation definition and point of separation. Now, the boundary layer separation is depends upon the pressure gradient. Depends upon the pressure gradient. If the pressure gradient varies one place over the boundary layer, one place the pressure gradient is negative, some points the pressure gradient is minimum, some points the pressure gradient is maximum or more than 0. So, the pressure gradient varies from one point to another point over the boundary layer. So, that first we should know the how to varies the pressure gradient from one point to another point, and before that pressure variation or pressure gradient, first we should know the Bernoulli's equation. Why? Because pressure gradient increases, automatically velocity gradient reduces. For that clarification, first we should know Bernoulli's equation. Right, this is one pipeline, varying dia pipeline. This is section 1-1, section 2-2. This is one datum line. This is Z1 distance from the center line of the pipe. This is also Z1 distance from the center line of the pipe. Bernoulli's equation states that, say this is the pressure P1, velocity V1 at section 1-1, pressure P2, velocity V2 at section 2-2. Bernoulli's equation states that the pressure head at section 1-1 plus velocity head at section 1-1 plus datum head at section 1-1 should be equal to pressure head at section 2-2 plus velocity head section 2-2 plus datum head at section 2-2. That is the Bernoulli's equation. Now, pressure head P1 by W at section 1-1, V1 square by 2G at section 1-1 plus Z1 is equal to P2 by W at section 2-2 plus V2 square by 2G at section 2-2 plus Z2. This is the Bernoulli's equation. Now, the Z1 and Z2 are same distance from the datum, therefore Z1 is equal to Z2. Now, pressure P1 by W plus V1 square by 2G is equal to P2 by W plus V2 square by 2G. Now, this is the pressure head, this is the velocity head. This is the pressure head at section 2-2, this is the velocity head at section 2-2. Now, it states that suppose the pressure head decreases, automatically velocity head increases, but sum of these two should be equal. Here also, if the pressure head increases, automatically velocity head should be decreases, the sum should be same value. That the Bernoulli's equation, as per the Bernoulli's equation, pressure head plus velocity head at section 1-1 must be equal to pressure head plus velocity head at section 2-2. Right, now this is the diagram, just you are going to see the diagram only, then next slide I will explain about the boundary layer separation. Now, this is one curved boundary, this is one curved boundary. The points over the curved boundary is A, B, C, S and D. Okay. And this is the boundary layer. This is the boundary layer. In this boundary layer, what is happening? The cross-sectional area at the point D is more, the cross-sectional area at point S is less as compared to D, and cross-sectional area at C is less as compared to S, and the cross-sectional area at B is very, very less as compared to C and as compared to D. Right? It means that the cross-sectional area increases gradually, automatically the velocity is decreases here, velocity is decreases here. Here the cross-sectional area is less, automatically velocity is high velocity, high accelerate position at the starting point of the boundary layer. So, because of this velocity changes from high velocity to low velocity, automatically the pressure is also changes. Here the velocity is high at this point, the velocity is high at point B, automatically pressure is less. So that the pressure is at this point is the pressure gradient or pressure dou P by dou X with respect to along the length, with respect to distance, with respect to X axis. Therefore, dou P by dou X is less than 0. That means pressure gradient is less than 0 because the velocity is high. This is based on the Bernoulli's equation. Once pressure increases, velocity decreases, velocity increases, so automatically pressure decreases. Based on the Bernoulli's equation, the cross-sectional area is less at this point, automatically velocity is more. Once velocity is more, the pressure should be less than 0, or pressure gradient is equal to dou P by dou x is less than 0. Then gradually the cross-sectional area increases, velocity decreases compared with this point. At this point velocity is less, automatically velocity decreases, pressure should be slowly increases. At this point the pressure is negative value less than 0, gradually that pressure reaches to the minimum value here. The velocity is reduces here, pressure is increases, and that pressure gradient from negative to reaches to minimum pressure at this point. And again the boundary layer cross-sectional area gradually increases, cross-sectional area gradually increases, the velocity is also reduces here compared with this point, velocity reduces automatically, velocity reduces here, velocity reduces, so pressure gradient increases, so therefore dou P by dou x is more than 0. Beyond this point again pressure increases, velocity decreases. This is the phenomena related to boundary layer theory, right? Now we are going to discuss the boundary layer separation, how to boundary layer is separated from the boundary, what are the regions, why the boundary layer is separated from this one, what conditions existing there, that we are going to learn here. Now we are going to take one curved surface A, B, C, S, D. Okay. On this curved surface, we know this is the boundary layer. This is the boundary layer. Now we are going to take one region, that is A, B, C. Now we are going to one region, that is A, B, C. This is the one region. This is one region. In this region, the C, what is happening here? The cross-sectional area gradually increases within the boundary layer thickness, so that at point C, the cross-sectional area is very, very small as compared with the point D. Are you clear? The cross-sectional area at point D is too high as compared with the point C. So that now we are going to take this zone A, B, C. In this zone, the cross-sectional area is very, very small as compared with the curved surface C, S, D. Therefore, the cross-sectional area is very, very small in this zone, that is A, B, C. Automatically, the velocity in this zone is increases. The velocity in this zone is high as compared with the curved surface C, S, D. Once the velocity is high in this zone, automatically what is happening? Pressure is reduces. Velocity is high because of the less cross-sectional area, automatically pressure reduces. Therefore, the pressure gradient dou P by dou x is less than 0. Velocity is high in this zone, automatically pressure is less. Once the pressure is less, pressure gradient is less than 0, right? Now the zone B to C, the velocity is more as compared with this zone. Therefore, the velocity is high, the pressure is reduces, and the pressure gradient is less than 0. Now next point, as long as the dP by dx, as long as the dP by dx is less than 0, because velocity is high, dP by dx is less than 0, the boundary layer will be moved in the forward direction. Very clear. dP by dx is less than 0, velocity is high, automatically the boundary layer will be moved towards forward direction. That is the condition, right? This is regarding the surface A, B, C. As per this diagram, as per this statement, what we have gained at point B to point C, the cross sectional area is very small as compared with the cross sectional area CSD, this curve. Therefore, velocity is more, pressure is less, automatically pressure gradient in this zone is less than 0 or negative. Right, as long as that pressure gradient is less than 0, the boundary layer should be moved towards forward direction. This is regarding the zone ABC. Now we are going to take the curved surface CSD. CSD. This is the zone we are going to take into consideration. This is the zone. Right. So this is the zone over the curved surface CSD, the boundary layer thickness is gradually increases. Once the boundary layer thickness increases, automatically the cross-sectional area within the boundary layer thickness also increases from C to D. The cross-sectional area in this zone is more as compared with this zone. What is happening? The cross-sectional area is more, automatically the velocity gradually decreases towards or along the length of the plate or in the direction of the motion of the fluid. Cross-sectional area increases, velocity reduces, automatically the pressure will be gradually increases and reaches to maximum value. Right? In this case, this is the cross-sectional area increases, velocity reduces, automatically pressure increases, then pressure gradient dP by dx is also positive value. So that at point C, the pressure is minimum pressure, this side the pressure is negative value, from point C the pressure is minimum, from point C to point S the pressure increases and reaches to positive value, that is more than dP by dx is more than 0. Right? This is about the curved surface CSD. Right? In this zone, right, pressure gradient is positive. Next point, how to separate the boundary layer from the surface of the boundary. This is the point we want to conclude here. Now, what is happening? So, here in this point, the velocity is high, pressure is low, automatically dP by dx is less than 0. And here the pressure gradually increases, velocity gradually reduces. In this zone completely velocity increases, in this zone velocity completely reduces, automatically pressure increases, so that the pressure gradient at this point dP by dx is more than 0. Right? What is happening at point S? At point S, the combined effect of the positive pressure gradient, at point S, the combined effect of the positive pressure gradient, because at point S is the dP by dx or the pressure gradient is more than 0, combined effect of positive pressure gradient and surface resistance at this point reduces the momentum of the flowing fluid. At point S, the combined effect of the positive pressure gradient and the surface resistance reduces the momentum of the flowing fluid, automatically problem creates. Momentum of flowing fluid reduces, automatically problem creates. At certain point, the momentum of the flowing fluid cannot be able to resist the surface and the boundary layer starts separating from the point S. Automatically the boundary layer can be separated from the point S like this. Beyond the point S, the flow in this boundary layer is reverse case. Automatically the velocity gradient in this zone du by dy is negative. The velocity gradient in that zone is negative because the flow beyond the point S is reverse direction. This is about the boundary layer separation. S, that is the boundary layer separation, is determined from these equations. How that boundary layer is separated? or boundary layer is not separated or ready to separate the boundary layer. If the du by dx, if the du by dx at y is equal to 0 is negative, what is happening? Velocity gradient is negative. That means pressure gradient is positive. Once the pressure gradient is positive, pressure is gradually increases, pressure gradient is positive. What is happening? Break at that point, because if we are going to take one balloon, the balloon is filled with air. If that is stressed with high pressure, because of the high pressure, automatically that will be collapsed. What is happening? The pressure increases, automatically that balloon collapse. Like that, here also boundary layer takes separation from the surface of the boundary. Now, the velocity gradient du by dy at y is equal to 0 is negative. Velocity gradient is negative, that means pressure gradient is positive. At the pressure gradient is positive, what is happening? Boundary layer separation takes place. Boundary layer separation takes place. And another case, du by dy at y is equal to 0, du by dy is equal to 0, that is verge of separation, ready to separation of the boundary layer. If the du by dy is equal to 0, automatically the pressure is minimum, automatically pressure gradient is minimum. At that stage, the boundary layer is ready to separate from the surface of the boundary. Right? And the next one, du by dy is positive at y is equal to 0. Du by dy is equal to positive means du by dy, that velocity gradient is positive, means automatically the pressure is very minimum. Pressure is minimum, automatically pressure gradient is negative value. dp by dx is negative. Once the pressure gradient is negative, that place there is no separation. Once the pressure gradient is negative or dp by dx is less than 0, automatically the boundary layer should be moved towards forward direction. There is no separation takes place. dy by dx is equal to positive. These three statements, these three equations concludes the boundary layer is existing or boundary layer separation takes place, boundary layer separation not to takes place. Right, now we are going to solve one problem related to boundary layer separation. Right, for the following velocity profiles, determine the flow has separated or on the verge of separation or separated from the boundary. So, first equation, they have given one velocity profile, that is small u by capital U equal to 3 by 2 y by delta minus 1 by 2 y by delta cube. Velocity profile they have given. Based on this velocity profile, we are going to decide boundary layer separates from the boundary or boundary layer ready to take boundary layer separation, boundary layer along with the surface of the solid body. Now, small u equal to capital U, 3 capital U divided by 2 y divided by delta into capital U minus capital U divided by 2 into y by delta whole cube. Right? Now, differentiate with respect to y on both sides. So, therefore, du by dy is equal to differentiation of this equation with respect to y. 3u by 2 is the constant. 3u by 2 is the constant. Differentiation of y by delta with respect to y, this is equal to 1 by delta minus u, free stream velocity constant, u by 2, and differentiation of y by delta whole cube equal to 3y square divided by delta into 1 by delta. Right? Now, du by dy, that is the velocity gradient is equal to 3u by 2 into 1 by delta minus u by 2 or 3u by 2 y square divided by delta into 1 by delta. Are you clear? This is the velocity profile given. Therefore, velocity of the within the boundary layer equal to 3u divided by this u move this side, same equation here. Once that is differentiating both sides, the equation differentiating with respect to y, then this value differentiating with respect to y, we are having this value. Du by dy at y is equal to 0, what is happening? At y is equal to 0, what is happening? At y is equal to 0, here there is no y component, 3u divided by 2, 3u divided by 2 into delta, right, minus 3u by 2, 3u by 2. In place of y we are going to take 0, 0 square divided by delta into 1 by delta. Right, from this equation du by dy is equal to 3u divided by 2 delta minus, this is 0, entire this term is 0, therefore du by dy is equal to 3u divided by 2 delta. What is happening here? At y is equal to 0, du by dy is equal to 3u divided by 2 delta. That means the value is positive. There is no separation of the boundary layer, the flow contact with the boundary surface. Next one, this is another profile, small u by capital U equal to 2 into y by delta square minus y by delta cube. Now same way, u equal to, small u equal to 2u y by delta square minus u y divided by delta cube. Right, now u equal to, we have one equation. Now the differentiate with respect to y, du by dy is equal to 2u is the constant. The differentiation of y by delta square equal to 2y by delta into 1 by delta. Right, the differentiation of u is the constant, y by delta whole cube, difference with respect to y, this is equal to 3y square divided by delta into 1 by delta. This is the value of du by dy. At du by dy, that is velocity gradient, du by dy at y is equal to 0, du by dy at y is equal to 0, what is happening? So in this term we are having y we are going to provide 0, automatically this entire term is 0, minus here also we are having y, so this entire term is also 0. The finally du by dy velocity gradient is equal to 0 at y is equal to 0. In this case, verge of separation, ready to take separation from the solid boundary. Okay. And last equation they have given, that is equal to small u divided by capital U is equal to minus 2 y by delta plus 1 by 2 y by delta square. This is also same way, small u velocity of the flow within the boundary layer equal to this u minus 2u y divided by delta plus 1 by 2 y by delta square. Now differentiate the equation both sides with respect to y. Therefore du by dy is equal to 2u, y by delta differentiate with respect to y, this is equal to 1 by delta plus 1 by 2, this is u also here, u, this u goes this side, u divided by 2 y square, that is equal to 2 y by delta. right? This is the differentiation with respect to y. Now y is equal to 0, y is equal to 0, du by dy is equal to. So here there is this is minus. Here there is no y term. This is equal to minus 2u by delta plus. Here y is equal to 0, automatically this entire term is 0. Therefore, du by dy at y is equal to 0, du by dy is equal to minus 2u by delta. Here what is happening? The velocity gradient at y is equal to 0 is the negative value. Velocity gradient is negative value, automatically boundary layer separation takes place, right? This is about boundary layer separation theory and related problem.